Hello everyone, my name is Carter. This is 1996, step 1, question 1, the theme of differentiation. Okay, let's get straight into this. So a cylindrical biscuit tin has volume V and surface area S. And when we talk about surface area of that biscuit tin, we are including the ends. Obviously, with the cylinder, you have these sort of two circular ends, these two circular faces connected to this sort of curved face. So like these are the circular faces. This is one, this is two. So you got one circular face on each end of the cylinder, and then a curved face connecting those two circular faces. And so when we calculate the surface area of that biscuit tin, obviously you want to find the total area on the outside of the biscuit tin. And so not only do we calculate the area of that sort of curved face, we also calculate the areas of the two circular faces and add that to the area of the curved face to get our total surface area. Okay, and so we need to show that first. We need to first show that the minimum possible surface area for a given value of b is equal to s, which is 3 times the cube root of 2 pi v squared. So, well, first things first, let's try and really understand what this is saying. Ultimately, what this is saying is that my biscuit tin has some fixed volume, so that's not going to change. So, as an example, it could be something like 400 pi centimeters cubed. Okay, and the volume of a cylinder is given by pi r squared h. That's an important formula here. And the reason why that volume is the volume of a cylinder is given by pi r squared h, like if you forgot and you wanted to somehow remember it for the in the exam, you can just think of a cylinder as sort of a circular prism, right? Effectively, it's just lots of like sort of circles of the same size stacked on each other, right? And so ultimately, with prisms, you just calculate the area of the face, one of the faces at the end of the prism, and then multiply that by the cross-sectional length, which in this case is just h, it's height. Okay, so clearly the area of the circle, the circular face on the end of the prism is just pi r squared, and the cross-sectional length is simply just h, right? Just our height. So clearly, therefore, the volume of our cylinder will be pi r squared h. So I should really say volume of cylinder. And so let's suppose that my volume is going to be acting up. Hold on. Let's suppose that my volume was sort of 400 pi, right? So let's just say that my volume is equal to some fixed constant V0, which is 400 pi. Then clearly we could have R being 20, we'll say centimeters cubed. We could have R being 20 centimeters and H being 1 centimeter, or we could have R being 10 centimeters and H being 4 centimeters, right? But ultimately, the only condition really is that whatever R and H are, when I plug them into my volume formula, pi r squared h, I'm going to get this fixed volume V0, whatever it is. It doesn't actually have to be 400 pi. I just chose an example. But ultimately, it's saying that if I fix my volume, so if my volume is staying the same, but my values of R and H can change, right? You can see in this case, there are two different possibilities. And there's actually infinitely many possibilities for R and H. If you pick an R, you can, a lot of the time, find the H that gives you the given volume that you want, and you plug it into the volume formula. So ultimately, the point of the question is that we're fixing this volume, so the volume isn't changing, but the surface area can change because R and ultimately H can both change. So the question is, if I fix my volume, what is the smallest possible surface area I could have for that volume of my biscuit tin? And so ultimately, I think at this point, it's probably good to also list the equation for the surface area of a cylinder, because I don't know what I'm doing right now. I'm trying to like, yeah, yeah. Okay. Wait, hold on a second. Yeah. Effectively, yeah, it's a good point in time now to list the equation for the surface area of a cylinder. And obviously, we're calling this volume V0. So V0 just is like fixed constant, right? So it's just some fixed constant. And the formula for a surface area of our cylinder is going to be given by, so obviously we need to add, so because the question specifies that we're including the ends, we need to add the areas of those two circular faces on. So the area of a circle is just pi r squared. we have two circular faces in our cylinder, so it's going to be pi r squared plus pi r squared, which is 2 pi r squared. So that's the contribution from the circles on the ends of the cylinder. But the curved face is actually going to add an extra 2 pi r h. And the reason for this is simply because actually this curved face can be sort of unwinded to give you a rectangle, and the length of that rectangle, effectively, you get a rectangle. The length of that rectangle will be the circumference of the sort of circular face on the top, which is given by obviously 2 pi r or pi d, right? Because 2 times the radius just gives you the diameter. This is just going to be 2 pi r, and the breadth of that rectangle will just simply be the height of the cylinder, right? So whenever you sort of unwind that curved face, you will indeed get a rectangle with these dimensions, and clearly the area of that rectangle would just be 2 pi r times h, 2 pi r h. So effectively, this 2 pi r squared is the circular faces on the end, and the 2 pi r h is the curved face connecting them. So that accounts for every single sort of piece of area on the outside of the biscuit tin, and so therefore our surface area of the cylinder is 2 pi r squared plus 2 pi r h, right? Okay. Okay. So ultimately, what we want to now do is we want to minimize the surface area if I have a fixed volume. Um, and it's probably going to be easier for us to work with one variable. So a good idea is to sort of rearrange our volume equation for, let's just say, the easiest variable to rearrange for, which is h, and then plug that h into the surface area equation, and then do some stuff with that. So effectively, from our volume equation, we have that h is simply just v naught divided by pi r squared, right? So we've solved for our height as a function of r, and we can plug this back into, so we substitute this into our surface area equation. Let me zoom out. We substitute this into our surface area equation. So ultimately what we get, and by the way, the surface area, we just call it S in this question. So effectively what we get is we get S is equal to 2 pi r squared, add 2 pi r times h, and our h is simply just our v naught. Remember, v naught is a constant here. It's not changing. So v naught divided by pi r squared is our height, right? So effectively we can cancel out these pi's, we can cancel out one of the r's, and we just get that this is just the same thing as 2 pi r squared add 2v naught divided by r. So that's our surface area just as a function of r. Obviously, we also have this constant v naught, which we don't know, but that's okay because it's asked us to effectively write our minimal surface area in terms of that constant v naught. So we don't need to like solve for it or anything like that. Effectively, well, the theme is differentiation, so we're going to have to somehow get some differentiation in there. And the clue word that I've highlighted is minimum. So if you want to find the minimum possible surface area, we have a function which represents our surface area as a function of the radius, then clearly a good idea would be to differentiate that and set that to be 0, right? Because then you can find your stationary points, the value of r, which either minimizes, maximizes the surface area, or just is a stationary point of that function of r. So in order to do that, we need to basically differentiate s with respect to r and set that to be 0, right? That's just how you like have been doing this in your studies, right? In an A level. So let's just go and do that. So obviously when we differentiate s with respect to r, what we get is we get 4 pi r, right? Because 2 pi is a constant and r squared, the derivative is just 2r. And that's just simple power rule. Obviously, the 2v naught over r, so we can think about that. So you're trying to find ddr of 2v naught r to the minus 1, since r to the minus 1 is simply just 1 over r. And 2v naught is just a constant, and the r to the minus 1, again, is just a power rule usage. So this just gives us minus 2v naught r to the minus 2, right? Because you bring the minus 1 down to the front, and you minus 1 from the power. So minus 1 gives you minus 2. And this can also be written as minus 2v naught divided by r squared. So effectively, the derivative of our surface area with respect to the radius gives us 4 pi r minus 2v naught divided by r squared. We set that to be 0. Okay, so now let's solve for r, since that's our variable. And the R that we solve for will be the R that minimizes our surface area effectively. So this implies that 4 pi r is equal to 2v naught divided by r squared. So you multiply by r squared, and that gives us that pi r cubed is equal to 2v naught, right? Then you can divide that by pi and cube root it to get r. So it's not the nicest answer, but it is the answer that we're going to have to work with. So we're going to get the cube root, or whenever you write something like the cube root of something, you can also write that something to the power of a third, right? Because x to the power of a third is equivalent to the cube root of x. So we can say, therefore, that r is equal to 2v naught divided by pi, effectively. No, sorry, it should be 4 pi r cubed. There we go. So that we're going to get 2v naught divided by 4 pi to the power of a third. And that effectively just gives us v naught divided by 2 pi to the power of a third. And this is our value of r that minimizes our surface area. And technically, we don't know it minimizes our surface area. We just know that it's effectively going to give a stationary point in our sort of surface area function. But it is kind of inferred from context. And if you want to check, you could technically take the second derivative and plug that value of r in and see if it's for a minimum, you need it to be positive. So if you have that second derivative being positive, you get a minimum, right? But it's kind of inferred from the question. We only have one value of r from this. So if it wasn't a minimum, then we wouldn't be able to sort of do anything, right? It would be it wouldn't really make sense. I'm not sure if they want you to take second derivative, but at least when I intended the question, I just sort of implicitly assumed that was the minimum, and you get the right answer by assuming that. So it is the minimum, right? But yeah, I guess you'd have to do a little bit more checks, just to basically just you'd have to do a little bit more just as a sanity check to make sure that's a minimum. But like as far as we're concerned, the question's asking for a minimum. We have one value, which is a stationary point. It's probably going to be the minimum, right? Anyway, so we can substitute. So I'm not going to do the sanity check, but you can do that yourself if you're interested. So we can substitute R into S, right? Because we're trying to find what that minimal surface area is. So that effectively just gives us 2 pi multiplied by v naught divided by 2 pi to the power of a third, all squared. So that gives us v naught divided by 2 pi to the power of 2/3, right? So if you have v naught divided by 2 pi to the power of a third, and you square that, you can just multiply these two powers, just indices laws. Okay, so this is just us plugging our value of r back into S, and then we plus 2v naught divided by r. So 2v naught divided by r in this case, and our r is 2 pi to the power of a third, right? So you could write this. This is the same thing as 2v naught divided by v naught to the power of a third divided by 2 pi to the power of a third. So obviously, whenever you divide a fraction, you can multiply by the reciprocal. So you're just going to get multiplied by 2 pi to the power of a third over v to the power of a third over v to the power of a third. If it lets me do this, or v naught to the power of a third. And effectively then, because you have the top and bottom both something to the power of a third, you could just bring that into these sort of brackets and write it as one fraction to the power of a third. So effectively, this second term, this 2v naught divided by r, is just equivalent to 2v naught multiplied by 2 pi divided by v naught to the power of a third. Okay, so that's that, right? And this is our surface area S. This is our minimal surface area S. But obviously, it's not in the form that we want it to be in just yet. Because obviously, what we want, we go back up, we want to get 3 times 2 pi v naught squared to the power of a third. So we don't really have that yet, but we can get that by effectively bringing everything into sort of by bringing everything as something to the power of a third with some coefficient in front. So what I mean by that is obviously 2 pi, you could rewrite it as 8 pi cubed to the power of a third. V naught over 2 pi to the power of 2/3 is the same as V naught over 2 pi squared to the power of a third. So we can say that's V naught squared over 4 pi squared to the power of a third, right? Because again, all I'm saying here, just to clarify, is that V naught over 2 pi to the power of 2/3 is equal to V naught over 2 pi squared and then to the power of a third, right? Which is completely valid. That's just indices laws. So hopefully you know what I'm saying. And so then we have those two things, and the 2v0, we can write that as 8v0 cubed to the power of a third. That gives us 8v0 cubed to the power of a third, multiplied by 2 pi divided by v0 to the power of a third. This gives us our minimal surface area S, right? And now, because we have two things combined to the third, so x to the third multiplied by y to the third is always going to give us just xy to the power of a third. So we can combine those things into one bracket, which is useful. So effectively, in this case, it's just equivalent to having 8 pi cubed v naught squared divided by 4 pi squared to the power of a third. Add 8 v naught cubed multiplied by 2 pi divided by v naught to the power of a third, right? So obviously we can simplify most of this. So this is going to give us, we can cancel the 8 with the 4, pi cubed with pi squared, that just gives us a pi. So in that first bracket, I just get 2 pi v naught to the power of a third. In that second bracket, I can cancel out a v naught, so I get v naught squared. And so in that bracket, I get add 8 times 2 pi v naught squared to the power of a third, right? Obviously, I've written it like this as 8 times 2 pi v naught squared to the power of a third, because then we can write that as 8 to the power of a third times 2 pi v naught squared to the power of a third, right? And 8 to the power of a third is just 2, so I can just write this entire thing as 2 lots of 2 pi v naught to the power of a third. So let's just do that. So that's just equal to 2 times 2 pi v naught squared all to the power of a third, right? And clearly this, the thing, so we basically just have 2 pi, this should be v naught squared to the power of a third, add 2 lots of 2 pi v naught squared to the power of a third. So those terms are exactly the same. It's just like x plus 2x. So we're just going to get 3 lots of that, right? We're just going to get 3 lots of 2 pi v naught squared to the power of a third. And just hopefully that's what we expected, exactly, right? So it's saying that we need to show that the minimal surface area is 3 lots of 2 pi v naught squared to the power of a third, and that is exactly what we got. So that's the first part of the question done and dusted. The second part of the question says, for this value of S, so the volume of the largest sphere which can fit inside the tin is 2/3 pi. 2/3 v. So, okay, how are we going to do that? Or, well, in this case, by the way, the v, I'm just writing it as v naught. So it's just our fixed constant for the volume. How are we going to show that the volume of the largest sphere which can fit inside the tin is 2/3 v? Well, the first things first, let's just make clear what we're trying to do here. So we have our biscuit tin, and I'm trying to just shove a sort of sphere, right? Just a 3D kind of like a ball, and we're just kind of shoving it in, right, to our biscuit tin. And we want to basically find the largest possible sphere which we can shove into the tin feasibly, and find its volume, right? So in order to do that, we're going to need to think a little bit, but we can sort of reduce this problem to sort of a 2D problem if we just take the cross sections of both the sphere and the cylinder, right? So if I just sort of move to the right here, so taking cross sections of the cylinder and sphere, taking cross sections of the cylinder and sphere, we have the diagrams below. So obviously, whenever you take a cross section of a cylinder, ultimately what you're going to get is you're going to get kind of this thing that I'm about to draw. So you're going to get like a rectangle, right, with these sort of circular faces coming out from the back of that sort of cylinder, right? And so all I'm doing here is I'm just slicing that cylinder directly in half, and now I'm getting this sort of rectangular cross section. And rectangles are pretty nice to work with, right? And if I were to shove my sphere inside that biscuit tin, there would be this sort of sphere inside the biscuit tin. So when I cut the biscuit tin in half, you'd also get the sphere being cut in half, and the cross section of the sphere just looks like some circle, right? So within this rectangle, we're trying to fit a circle. And so now the question is, if I'm maximizing the volume of that sphere, then effectively I'm trying to make this circle as big as possible. right? Um, I'm trying to basically just maximize the radius of my sphere, right? Since the volume of a sphere is equal to 4/3 pi r cubed, right? So effectively, if I can maximize my radius of the sphere, I can maximize my volume of the sphere, right? And maximizing my radius is equivalent to effectively maximizing making this circle as big as possible. Um, so before we do that, though, there's actually something important which we can notice. So when we were doing the differentiation stuff, we got to a point where we had this sort of 4 pi r minus 2v naught over r squared is equal to 0. For this particular value of r, we solved that we got v naught over 2 pi to the power of a third, right? Um, and also for the question, for the second part of the question, we're working with that surface area S, right? So effectively, the surface area, the minimal possible surface area that we found in the first part of the question, we're keeping for the second part of the question, right? And so we know that the radius, therefore, is going to be this value that we found because we're literally working with the specific biscuit tin that has the minimal possible surface area for that fixed volume. So we know that r is given by this value, but more importantly, right, if you look over here at what we have this 4 pi r is equal to 2v naught over r squared. So we can actually solve for v naught, and we clearly get that 4 pi r cubed is equal to 2v naught, right? And more specifically, we get that v naught is equal to 2 pi r cubed, right? So when we get that v naught is equal to 2 pi r cubed, we can just plug this back into our typical volume formula, right? So plugging that back into our volume formula, since we have that v naught is equal to 2 pi r cubed, right? This is just our volume, right? So whatever the radius is, it's just equal to 2 pi. So it's equal to that value cubed multiplied by 2 pi. Okay. And obviously, we also know that the volume of our cylinder, V naught, is also equal to pi r squared h, right? From the beginning, just from the typical volume of a cylinder. So we can just set this is equal to pi r squared h and effectively just get all the r's on one side and all the h's on another. So we can cancel out these pi's, we can cancel out sort of this r squared term. And so what we end up getting, what we can see from this is that we get that 2r is equal to h, or in other words, the height of the cylinder is equal to 2 times the radius of the circles on the ends of the cylinder. So for this specific configuration, remember, because we're keeping the same configuration as we sort of solved for in the first part of the question, so with the minimal surface area, so the height is equal to 2 times the radius. So if I think about this rectangle I have here, this is just equal to 2r, and this is obviously just the diameter of our circle, which is also equal to 2r, right? So that is if we're slicing directly in the middle. Okay, and then from that, well, what do we know from that, right? So if I center my circle literally in the center of this rectangle here, so directly below the center of the circles and at the sort of top and bottom of the biscuit tin, then what I'm going to notice is that sort of this distance here, that has to be r, since it's just half of the 2r that I have sort of going up, and the half of the 2r, which is effectively like the length of my rectangle. And I also know that sort of this distance here is going to be r, right? Because again, it's kind of just like the radius of my circle directly above it, but just like moved down. I haven't really like stretched it out. I haven't done anything to it. So this distance here is also clearly going to be r, right? So actually, what I can do is I can fit a circle with radius r that just touches the four sides of my rectangular cross section, right? I know it doesn't look like a circle because I didn't draw it properly, but it would be a circle in this specific configuration. So I can actually just fit a circle exactly touching four of the sides of my rectangle, right? And it's clear from here that I cannot have a circle any bigger than this fitting within that rectangular cross section. Because if I did, then the radius would have to be larger, right? And if I'm thinking about a circle of sort of larger area, I would need to have a larger radius. But if I have a larger radius, then it's going to go past this point here, right? If I just sort of make a sort of horizontal movement. Um, so clearly, if I have sort of any sort of larger circle, then it will have a larger radius, and that larger radius will take me to some point like out here, right? Which clearly, and maybe some point over here, and some point over here, some point over here, which clearly just extends past the sort of biscuit tin, right? So there's just no way that I'd be able to make the circle any bigger. So we know that the circle that so we know that the largest possible circle, or really, and by the way, this circle, this sort of um, this circular cross section that we're fitting inside this rectangular cross section, is actually um, also telling us about the sphere, right? Because that's ultimately the question. We're trying to fit the largest possible sphere within our biscuit tin, right? So clearly, we know that the largest possible sphere also has to have radius r, right? Since this circle is just the cross section of that sphere and it has radius r, the sphere itself will have radius r. So we know that the largest possible sphere, so we know that largest possible sphere, don't worry about my English, largest possible sphere has radius r, has radius r, and obviously we know that our value of r is equal to, what was it, v naught divided by 2 pi, the power of a third. So from here, we just calculate our volume. So our volume of sphere is equal to 4 thirds multiplied by pi r cubed. And this cubed, so effectively what this is going to give us is 4 thirds multiplied by pi times v naught over 2 pi, right? Because we had v naught over 2 pi to the power of a third, or the cube root of v naught over 2 pi. Then we just cubed it. So the cube root cubed just cancels out the cube root. You just get v naught over 2 pi. So effectively, we can see that these pi's cancel out, factor of 2 gets cancelled out, and so what we end up getting is indeed our 2 thirds v naught, which is what we expected. So we've shown the volume of the largest possible sphere which we can fit inside our pin for that given surface area and fixed volume is indeed 2 thirds that fixed volume. Okay, we also now, so the last part of the question, we need to find the volume of the smallest sphere into which the tin fits. So in the previous question, we were shoving a sphere into our tin. Now we're shoving a tin into our sphere. So we're just making the sphere as small as possible such that we can fit our tin within it. So this actually looks exactly the same. So we can use kind of the same idea with the cross section. So using the same cross-sectional idea, using the same cross-sectional idea, we have the diagrams below. Right? Or really I should say just a diagram, because I only did one diagram. I'll fix that. I'll be grammatically correct, and I'll fix that diagram before the diagram and this the diagram. Effectively this time, right? Because last time we had a rectangle with a circle inside it. This time we're gonna have a circle with a rectangle inside it, right? So we're just gonna put our rectangle inside here. And obviously we have the center of our sort of rectangular cross section being the center of the circle. And another thing which we can notice is that sort of longest possible distance from that center of the um, rectangular cross section is going to be to the sort of corners of the rectangle here, right? So the longest possible distance I could walk from the center of my rectangular cross section to another point on that rectangular cross section is indeed that diagonal. I won't formally prove that, but it shouldn't be too sort of hard to see. You can see that in this case, right? If I just sort of like shrunk my rectangular cross section in place, then clearly those like it would fit inside the circle. But if I make it bigger and bigger, those 4 points are going to be the first to touch the sort of sides of my circle, right? For some fixed circle size. So effectively, what we're now trying to do is trying to make the circle as small as possible, such that that biscuit tin fits within it, right? But it becomes clear that if I make my circle any smaller than this, right, this specific configuration I have here, where it touches exactly those 4 sides of my rectangular cross section, if I make my circle any smaller than this, then I'm going to meet problems because simply this is my radius here, right? This is the radius of my circle. If I make it any smaller than this, I'm going to like cut off a bit of the sort of rectangular cross section. So that is going to be a big problem, right? Because I'm going to have bits like here I didn't catch, here I didn't catch, here I didn't catch, and here I didn't catch. So I'm therefore going to be somehow just like, yeah, my basically my biscuit tin will cut through my sphere, which is not allowed. So it needs to fit exactly within my sphere. So it becomes very clear that if I make my sort of circular cross section of the sphere any smaller, then it just won't do. It's not good enough. So this is the exact configuration which we're looking for. For this configuration, obviously, we already know that since we already have the biscuit tin, it's exactly the same as in the previous part of the question. So the height of the biscuit tin is just 2r, right? And we obviously also know that this length here is 2r as well. And same as before, we still know that this length here is r, since it's just half of the 2r on the bottom, right? And we also know that this height here is r, right? And sorry, I said r over here, but I should have really said capital R. But capital R is obviously the radius of this sphere that we care about, right? But it becomes clear because this angle here is clearly 90 degrees, right? The horizontal and the vertical are 90 degrees to each other. So clearly, it becomes clear that the radius of the circle that we care about, in other words, r squared, is equal to lowercase r squared add lowercase r squared. It's just Pythagoras' theorem. It's just Pythagoras' theorem. Pythagoras is theorem. I don't know why my pen is breaking up, but that's okay. So it becomes clear that the radius capital R that we want is simply just equal to 2 times the lowercase sort of radius, or the capital R radius that we want squared is equal to 2 times the lowercase radius r, the lowercase r radius that we already had for our sort of cylinder squared. And so when we square root both sides, effectively what we're going to get is that r is equal to the capital R is equal to the square root of 2 times the lowercase r. So the radius of our minimal sort of sphere, which can enclose the biscuit tin within it, has to be the square root of 2 times the radius of the circular faces on our cylinder, right? And from here, we already know that what the value of r is. It's just v naught divided by 2 pi, the power of a third. So we can calculate the volume, since we already know, we can calculate the volume of our sphere, right? Since the radius of our sphere is just given by the square root of 2r, right? Because the radius of our sphere is the same as the radius of our circular cross-section of our sphere. So the volume of our sphere is equal to 4/3 pi r cubed, and this just gives us 4/3 pi times the square root of 2 cubed times v naught divided by 2 pi, right? Since the cube root of v naught divided by 2 pi cubed is just v naught divided by 2 pi. So the square root of 2 cubed is the square root of 2 times square root of 2 times square root of 2. The square root of 2 times square root of 2 is just 2, and the square root of 2 is 2 root 2. So we're going to get here 4 over 3 pi times 2 root 2 times v naught divided by 2 pi. So we're going to get a factor of 2, cancel out, the pi cancels out, and we end up getting here is 4 root 2 over 3 v naught. So the volume of our smallest possible sphere, which can enclose our cylinder, is indeed going to be 4 root 2 over 3 times the volume, the fixed volume of our biscuit tin. Very, very nice stuff. Let's just check we did everything. So yeah, cylindrical biscuit tin is volume V and surface area S. So the minimum possible surface area for a given value of V is that. We got that. For this value of S, show that the volume of the largest sphere which contains the tin is 2/3. We got that. 2/3 V, sorry. And find the volume of the smallest sphere into which the tin fits, which is indeed 4 root 2 over 3 V naught. Okay, awesome stuff. Thank you guys for watching.